All right, let's start. Let's do this. Okay, so um, this is the second to last episode where we're going to talk about the Mars Hub app chain. So today we're going to talk. So you see we have three custom modules in our Mars Hub chain. One being Safety Found, which we talked about last week, where we explained the overall layout of a Cosmos SDK module. So today we are going to go through the custom Gov module. Next week we go the most complex one, which is incentives. So yeah, and after that we can get into the outpost part of the protocol. If you're not very informed on this topic, Mars protocol now have a blockchain called Mars Hub, but we're also going to deploy our money market protocol in the form of wasm contracts on Osmosis and a number of other chains in the future. So we have been covering contents regarding the Mars Hub blockchain, but so this will be second to last episode. So yeah, afterwards we are going to jump into the outpost. So let's take a look at custom Gov. So custom Gov is basically the vanilla or the original Cosmos SDK governance module, but with one change, and that is, if you remember, we had this thing called a vesting contract, which performs token vesting for Mars builders. So there are a large number of tokens locked in that contract. We don't want those tokens to earn staking rewards, so that actual users who buy Mars token on the market can stake them and earn all the rewards. But we do want those builders to be able to vote in governance. So how do we implement that? We have to modify the vote tallying logic that the original governance module uses. So the difference is that in the original governance module, a user's voting power only comes from one source, and that is the amount of staked tokens the user stakes at the staking module. But now there are two sources, which are the stake tokens and the vesting tokens. So in the original governance module, the way it works is that if I stake with a validator, I delegate to that validator, the validator can vote. If the validator votes and I don't vote, then the amount of tokens I delegated to that validator will vote based on the validator's vote option. So if I don't vote, the validator votes yes, then my voting power goes to yes, right? If I do vote, if I vote differently, I vote no, then my vote will override the validator's vote. So my voting power will go to no, which is what I vote. So in our new custom governance module, there are two sources of voting power. The staked voting power behaves the same. The vesting voting power, what happens is if validator votes on my behalf, if the validator votes and I don't vote, then my stake token will vote whatever the validator votes, but my vesting power will not vote, right? So in other words, when I stake, I delegate my voting power of my staked token to the validator, but my vesting tokens voting power are not delegated to the validator, right? So let's take a look at this example. So Alice has 30 staked with a validator, 21 in a vesting contract, and Bob has 49 staked and 0 in vesting contract, and they are all staked with the same validator, right? So if this validator votes yes on a proposal and neither Alice and Bob vote, in this case, this first column, the stake tokens, which sums up to 79, are all going to vote yes, while the second column, the vesting tokens, which are 21, 0, they are not delegated to the validator. So these 21 tokens don't vote. So if the vote ends like this, then the final result would be 79 voting yes and 21 not voting. The vote passes. Now, if Alice votes no and Bob still don't vote, then Alice, for the staked part, Alice votes overrides the validator's vote, so it goes to no. This 21 also goes to no. Bob is not voting, so that 49 stays with the validator's choice. So the final result would be 51 no, 49 yes, and the vote is defeated. So that is how we want, that's how we intend this custom module to work. This part we can talk about later. So the question is, how do we customize the Gov module? So originally, the way I do it is I forked the Cosmos SDK repository. I modify the governance module there. And in my Go dependency file, what I would do is I would use this replace statement. So what I would do is I would replace github.com cosmos SDK with my fork. So that's like this, Mars protocol Cosmos SDK version something, some version. So basically like replaces the whole thing. But this turns out to be quite complex because our vesting contract is a wasm contract. The Cosmos SDK relies on a thing called SIM-app. If you have attended my validator workshop, you already know what SIM-app is. So it is a blockchain application contained in the Cosmos SDK repository, and the repository internally uses the SIM-app for testing. So if I modify the Cosmos SDK app in that repository, and if I modify the governance module in that repository and I want to do testing, I also need to add wasm to the SIM app because SIM app doesn't have wasm. So I have to add wasm to SIM app, and that breaks 100 different things. So the result is I want to introduce one particular module, but to complete that, I need to make changes to 100 different things, different modules across different folders, different aspects of the SDK. And that's really undesirable. So in the end, I opted to use this approach called a wrapper module. So the way it works is, so if you know object-oriented programming, there is a thing called inheritance. So let's see if there's some pseudocode here. If you have a parent class and the class has a method, let's say method 1, that's a function. The parent class has the second method 2 function, and you can define a child class. Class child is parent, something like this. And if you don't have anything here, then child is going to inherit method 1 and method 2. So you can call child method 1. Although you don't define method 1 for child, it inherits method 1 from parent. However, if you do define a method 1 with the same name and argument and input parameters that does something different from the parent's method 1, you are going to override this method 1. But you are still going to inherit all the other functions such as method 2. And that's exactly what we're going to do. So if we look at keeper, so if you have attended my last workshop, you know keeper is basically a bundle of functions that will perform read and write of the module's storage, stored data. So if you look at my keeper, my custom governance keeper, the first parameter of the keeper is the original vanilla gov keeper. So in Go language, if you put a class as the very first parameter of a class, and you don't give it a name, then what it means is that you set this one as a parent. So this is kind of weird Go syntax. In every other language, it would be something like type keeper struct extend this parent, right? This is more clear. This is my child. This is my parent. But in Go, the way you extend a class is you just put it in the very beginning. So that's just how Go works. So basically, I define a custom keeper class that inherits the gov keeper class. So if you look at the keeper, this is the original governance keeper, and it defines a function called tally. This is the function that when a governance poll finishes voting period, it tallies the vote. I'm going to write my custom tally function that overrides the original one, which is here. You see, they're pretty much the same, 99%, but I'm going to override this function so that when a governance proposal finishes, it will call my tally function, my custom one, instead of the original one. So that is basically the idea of how a wrapper module works. And as you can see, the benefit is that I don't need to change 100 different things. I only need to change this one thing that I want to change. So that is amazing. So that's the background part. So is there any question before I jump into exactly how this function works? Any question? No? All right. So if that's the case, then I say we start by looking at how the original tally votes works, and we just look at the differences. So the way it works is I first initializes a result, which is a map or dictionary if you're from the Python world. That maps the vote option to the amount of voting power that have voted for this vote option. So there are four vote options: yes, no, abstain, and veto. They're all initialized as 0. It also needs to count the total voting power, which we also initializes as 0. So as mentioned, when you stake your token with the staking module, your governance power is delegated to the validator. So we also need to enumerate all validators, and we basically grabs the voting power of all those validators. So a word here, how does enumeration works in Cosmos keepers? So the way it works is the keeper should define a function called iterate something that will take a context. So if you are from Cosmos wasm, the context is basically comparable to depths in wasm. So in depth, if you want to, in wasm, if you want to read or write the storage, you need a thing called depths.storage, right? In SDK, the storage is encapsulated in this context object. So this is your database. And you provide a function. So the function will take the data being enumerated and do something with that data and returns a Boolean on whether to stop. So the way it works is the keeper will give this function the data, and you see what the function does is it basically pushes the validator's info into this map, and it returns false, meaning don't stop. Enumerates all validators, don't stop. So by doing this, it enumerates all validators and put their data into this variable. So with that done, the governance keeper used the same approach to enumerate all votes, right? So for each vote, we grab the address of the voter and we grab all the delegations that this voter has made to validators. We iterate all those delegations and we do something like this. All right, so for each, well, so if this delegator has voted, that means the delegator wants to override the validator's vote, right? So in this case, what we do is we subtract the voting power from that validator because the validator's vote is being overridden. And we basically increment the total voting power, this counter up here, and we increment the results by the user's voting power, right? And here's a key point. We delete vote because after this vote has been tallied, it is useless. So we delete that. So once every voter has been tallied, we look at the validator votes. So these are votes that are not overridden by the voters. And we increment all those votes to the counters, the total voting power and individual option voting powers. So that completes the tallying process. And now what we do is we decide the voting result, right? And the comments here are pretty self-explanatory. If there's no staked coins for some reason, the proposal fails. So like if the total voting power is 0, that probably shouldn't happen unless the chain uses a different consensus algorithm that is not Tendermint. If you use proof of work, then you don't have staking token. I guess that works. If there is not enough quorum, so I take the total voting power that has voted, divide that by the total amount of tokens staked, and compare that with quorum. If that fails, that fails, right? Also, if it fails to meet enough quorum, we are going to slash the proposal creator's deposit and give that to the community pool. So the second return argument we have here is burn deposits. So if the proposal fails to meet quorum, we return true, and that burns the deposit. I'm not sure what's the rationale behind this, but that's what it does. If no one votes, everyone abstains, proposal fails. If more than 1/3 votes veto, proposal fails, and we burn the deposit. If more than half of the non-abstaining votes yes, proposal passes. Yeah, and otherwise, that means more than half non-abstaining votes have voted no, and it fails. But that's fair, so we don't burn the deposit. All right, so that's it. That's how the original governance tallying function works. Any questions on this? All right, nothing. Okay, so let's look at the differences. So we initialize the empty counter, the same. We grab the validator, the same. We grab the total amount of tokens that have been staked, that's the same. But we also grab all of the tokens that are in the vesting contract. And the total amount of token eligible for voting is the total amount of token that are staked plus the total amount of tokens that are invested. So in the original one, there's only the staked ones, but now we add up the vesting ones on top of that, right? So here's the function that I have created to allow the governance module to query the wasm contract. We'll talk about that later. But yeah, we start the total voting power that have voted to 0, and we iterate all votes. So these are all the same. These are the same. We deduct the validator's voting power if the user overrides their validator's vote. But additionally, we also handle the vesting voting power. Because the vesting voting power is not delegated to the validator, so we don't need to deduct anything from the validator on this regard. We just increment the voting power, okay, for that vote option. Yeah, and also I extracted some logics into this increment, this function called increment tally results. So this is just a helper function because if you look at the original code, this part and this part are identical, so they're repetitive code. So I just to improve the cleanliness of the code, I extracted it into a function. So, but it's the same. And now we delete the code, right? So, and a thing to note here is that ideally we want to use the delete vote function from the parent, right? Because the parent governance keeper has this delete vote function. Ideally, we just want to call the parent function. However, you see, this is a private function. It is not a public function. In Go language, if the first letter of the function is lowercase, it is private. If it is uppercase, then it is public, which is a super weird way of doing this. In every other normal language, what you do to make a function public is you just use a keyword called pub, like this, pub func, right? But in Go, for some reason, it is depending on whether it starts with an uppercase or lowercase. So just one more thing, weird design decision with Go. But in any case, the vanilla Cosmos SDK does not make this function public, so we cannot call it from our child, and that's super annoying. And because of that, in our child keeper, we need to redefine this delete vote function in order to delete vote. So, just some extra code that we shouldn't have to include if the original Cosmos SDK had made this one public. I actually asked Marco, the Cosmos SDK lead, why this is not public, and he didn't know. So I guess this is something they can fix. Yeah. But anyways, we tally the vote, we tally the voter, we tally the validators, and we determine the result. And that's all the same, except for I improved the comments to make it more readable, in my opinion. So that's the vote tallying. And the next topic is how do we query the wasm contract from our SDK module. So any question before we jump into that? Okay, nothing. All right, so let's take a look at our wasm module. So if you remember, the interface, the query interface of our contract is defined in Rust code by this struct. So I have exposed two query functions called voting power, which allows you to query the amount of tokens locked in the vesting contract that belongs to one user. I also have an enumerative query function called voting powers plural that allows you to enumerate all voting tokens locked in the vesting contract. And you can specify the pagination parameters if there are too many of them. And the response type is defined here. We return the user's address and we return the voting power that belongs to this user. And if you use the plural query, it returns an array or a vector of this response. So in order to allow the SDK module, which is written in Go language, to query this contract, it's a bit annoying, but we have to re-implement this thing in Go language. So the way to do that is here in the types folder, I create a file called vesting Go. And I am defining this here. I don't actually know why I need to define these. These are not queries. What if I comment them out? Ah, right. I need them in testing. Okay, so So these are only relevant in testing, but for the actual operation of our module, these are the ones that are relevant. So you see query message, we define a struct. So in Rust, it is an enum, but in Go, we don't have an enum. So what we do is we define a struct, but each member of the struct is a pointer. So the thing with pointer is that it can be nil. It can be a nil pointer. So the way we emulate an enum variant is we have this struct, but only one of the parameter is an actual pointer, while everything else is a nil. In that case, it represents the enum variant of that non-nil pointer, non-nil part. Okay. We also define the response type. So this is the query type, right? You see we have the start after and limit corresponding to start after and limit here. We also have the response type, which has user voting power. And here's our response type, user and voting power. Also, because the communication between of data between the wasm contract and the module are encoded in JSON. So the response data returned by the wasm contract is encoded in JSON, and the SDK module needs to decode that JSON. So and in JSON we use snake case to rename our data. So like in the JSON type, it is not uppercase voting, uppercase power. It is instead lowercase voting underscore lowercase powers, right? So in the Go code, we also have to define that in JSON, we want to rename this thing to voting power, right? So omit empty here, meaning we will allow this one to be nil. So if we don't omit empty, then the Go code will produce an error if this pointer is nil. So in order to emulate the enum type, we have to have omit empty. So that is basically the Go implementation of this Rust enum. And you can see it is much more complicated. All right, so here is the part where I query the contract. So this is the function. So the function takes the wasm keeper, the address of the contract to be queried, and the query, and it will return the query response. So there are multiple steps. So we take the query, we encode that to JSON. Second step, we pass in the query and the contract address to the wasm keeper, and the wasm keeper will do the query. And the response object is a binary byte, so raw bytes of the JSON. So the JSON is encoded into a string, and string is encoded into binary using the UTF-8 encoding. And at the very end, we decode the binary JSON into our voting response, and we return that response. So this is basically how you query a wasm contract in Go from an SDK module. So this is a helper function. We look at this later. So now we may have a large number of builders in that voting contract, in that vesting contract. So we might not be able to query the voting power of all of them in one go. That is why we have these pagination parameters. So we have to use a for loop to repetitively query all of them. And where did my file go? Here. So I have a function here to query all the tokens investing. So the way it works is we initialize a token investing that maps a user's address to their voting power. I also have a counter counts the total amount of voting powers investing contract. So we query once. We start by query once, and we increment these two counters. And now we look at the response returned by this result. If it is empty, that means we have finished querying all builders, then we break. If it is not empty, that means there are probably more builders to be queried. So we do the same query and implementing the counter again, and we keep looping this. So this basically is while true, basically. It's infinite loop until we break. So once we break, that means we have finished, and we just return the results. So looking at this increment voting power function, what it does is it takes the map, this map here. It takes this thing here, which is this. It takes a pointer here, so we can mutate it, and it takes the response. So basically, we just add the number to it, right? I have learned that this is actually not a very idiomatic way of doing Go code, that you take a pointer of a value and you mutate that value. It's actually not a very common way of coding in Go, but it is a very common way of coding in Rust. If you know, in Rust you can pass a mutable reference, right? You can pass this thing, and the function will mutate that. It's pretty common in Rust, in wasm, not very common in Go. So I just learned that, but it's fine. I'm from a Rust background. I'll do this. So that's the whole querying process. We also have a function. So this one is called get tokens investing. It will return the result and optionally an error. If there's no error, the error is a nil. So this one is just the same thing, but instead it doesn't return an error. If there's an error, it will panic. So it is called must get token investing. So that is also a Go custom of how to name contracts. If the contracts may panic, in case of failure, it called must do something. So that is Go. So in the tally function, we use this must get tokens investing contract function to query the contract and get the result. And if it fails, the whole thing panics and our chain faults. So hopefully there's no error. All right, so that's how vote tallying works. And now we take a look at how we trigger the vote tallying. So we define this file called ABCI, or called application binary something interface. Application something interface. I'm not quite sure about BC. So what it happens is we define this function called nBlocker. So nBlocker is a function that gets automatically executed at the end of every block. So this is something that's simply not possible if you're from Ethereum. Like on Ethereum, it is simply not possible that you can define functions to be automatically executed at a certain condition, right? It's just not possible. But with chains, with Cosmos app chains, we have this superpower. We can define actions to be automatically executed without costing any gas when it meets certain conditions, right? So we do this. This is for logging. This is for like benchmarking. Don't worry about them. So at the end of every block, remember the iterate pattern, right? We iterate all inactive proposals, and we just delete all inactive proposals. So when does a proposal becomes inactive? Well, if it doesn't receive enough amount of deposit within a time span, it is considered inactive and deleted. After that, we look at all the active proposals, and we tally it, right? Yeah, we tally it. And if the proposal is, now we get a bunch of results from that tally function. Now this is our custom tally function, not the original one, because it has been overwritten. So it returns whether the proposal passes, whether the deposit should be forfeited. and the detailed tally result. If the deposit is to be forfeited, we do that. Otherwise, we refund that. If it passes, we execute the proposal, right? We handle it. We emit some messages, some logging stuff. We save the final tallying result, and we set this proposal as inactive, right? And there may be some hooks to be done. We do that, and we do some logging. Oh, there should be an empty line here for aesthetics. But yeah, that's pretty much it. And in our module, the module, we all, like you see here, we define the app module. We also inherits everything from the gov module, but we override its end blocker, and we use our custom end blocker. So that's how it works. And in our app, we import our custom gov from our repository instead of from the Cosmos SDK gov, and we just replace the gov module in our app with our custom gov. So that's pretty much it. That's pretty much it. Now, after this, I'm going to show you guys a demonstration. But before I do that, is there any questions regarding this? All right. Empty line added. So if there's no question, I'm going to show you guys this thing in action. So I'm going to fire up the Mars blockchain. But before that, let's delete all the data that I had from the previous run. And let's first take a look at our Genesis state. So code Mars config Genesis Genesis.json. So this is our Genesis state. We have a validator account. We have a validator which has this much tokens staked. That's 100 tokens. Oh, and by the way, I reduced the governance voting period to 60 seconds, so you don't have to wait 5 minutes as we do in the previous sessions. And for the vesting contract, so these are the contract binary code, a bunch of stuff. For our contract, we only have one builder in this demonstration. And we create this vesting position for this builder, and the amount is 10 million Mars tokens. So what we are going to do is the validator will vote no, the builder will vote yes, and if it is with the vanilla governance module, this proposal should fail because in the vanilla one, this 10 million is not counted as voting power. Only the validator one is voting power. So no will be the only vote that fails, but with ours, this one should be successful. So let's try this. RSD start. Add a new terminal. So MarsD transaction gov submit proposal. So I want to do a text proposal. Copy the command. Title is test proposal. Description is my awesome proposal. Type is text. Deposit. Let me see what is the minimum deposit. Minimum deposit is 10 Mars. So Mars dev gas auto gas adjustments gas prices 0 password. All right, so Mars the query gov proposal 1. So let's say it is in voting period, and not we only have 1 minute. So let's do quickly Mars the transaction gov vote proposal 1. The validator votes no from validator, and copy the gas parameters. That's a no, and our builder will vote yes. Voted. So let's wait until the proposal finishes and see if it passes. So vote end time is 45:39. It should have already finished. Sometimes it delays a bit for some reason. It's still voting period. Right. I have customized Mars Chain's block time, so the block time is not 6 seconds as we had before. It's the block time is longer. So it takes some time for the next block to be produced, right? Because vote tallying only happens in n block, remember? So we have to have a block be produced before the vote is tallied. So yeah, so it is passed, and you can see no vote is 10. Actually, it's 100. The validator had 100, and the builder should have 10 million. Yeah. So yeah, 100 no from validator, 10 million yes from me, and it is passed. So yeah, everything works as intended. All right. So I guess that's it. That's all we have for governance module. Next time we talk about incentives module, and after that we talk about the wasm contract we are going to deploy on Osmosis. So if there's any question, please leave them here. If there's no, I think we can call this a day. And thank you for coming. I'm going to stay for 2-3 minutes, and if there's no question, I'll leave.
Thank you, Larry. Have a good day.